panels, and out of these 12 million metric tons, we will be only recycling 5 million metric tons, and 7 million metric ton is expected to obtain, that will be just remaining on the grounds, or maybe dumped to the open environment, or maybe it will go to the sea. So being as a researcher or being as an engineer, it's kind of our responsibility to provide some solution for such kind of increasing composite waste in the environment. Sorry. So, if we will talk about ultimate and proximate analysis and the motivation for the research, so let's start from the left side of the graph, where you are seeing on the extreme left corner, we have ultimate and proximate analysis for the wind turbine blades. And you are seeing we have very high portion of ash represented by the letter A, and then we have very high concentration of volatile matter that is indicated in the yellow color. So we can say if we can degrade this volatile matter, and in combination with carbon and hydrogen, the degradation of this volatile matter can produce some kind of secondary compounds. And on the other hand, that is ash, that is an inorganic materials. And in the case of wind turbine blades, it's actually the glass fibers. So if we will degrade volatile matter, and in conjunction with carbon and hydrogen, we can get some secondary compounds. In addition, we can also recover this glass fibers. So in the case of our wind turbine blades, our the main purpose is to degrade the volatile material, that is mostly the epoxy, different kind of polymers, and obtain this ash that is actually glass fibers. And for on the extreme right of this graph, for PV panels, you are seeing we have really less concentration of volatile matters, but we have very high concentration of the ash. So that was the representation that if we can degrade this volatile matter somehow, then we can obtain some useful products from this waste. So for this purpose, we try to introduce oxidative liquefaction. We will oxidative liquefaction, and we are expecting to get some oxygenated chemical compounds at the end of the process. So very shortly talking about oxidative liquefaction. In oxidative liquefaction, we are mixing the selected waste, mostly wind turbine blades or PV panels, with water and hydrogen peroxide. We are providing some sufficient temperature and pressure, and at the end of the process, definitely we are expecting some solid residues, because all of this waste can't be like converted to secondary compounds. Still we have some residues left, and we are expecting to get some oxygenated chemical compounds. And if we will talk about TGA and DTG analysis of selected waste, we performed TGA and DTG analysis at different heating rates from 2 Kelvin per minute to 16 Kelvin per minute. But here on the graphs, I am only showing the results that we obtained at 4 Kelvin per minute and 16 Kelvins per minute. So for the wind turbine blades and for PV panels, you are seeing the weight loss during the initial step is really minor. And in the case of wind turbine blades, it can be subjected to somehow some kind of low melting temperature polymers, for example polyethylene, polypropylene, some kind of this plastic during the first stage. But major stage of degradation mostly happens between 300 to 400 degrees centigrade, where it is subjected that this degradation is mainly due to the degradation of epoxy resin. On the other hand, if we will talk about PV waste, a very similar kind of observations were obtained, that we are getting the major degradation of over polymers around 400 degrees C, or maybe around 450 degrees C. And the initial weight loss can be subjected to the same kind of polymers that have less melting points. So now we will talk shortly about oxidative liquefaction. Every one of us almost have an idea about hydrothermal treatment. In hydrothermal treatment, we were just simply mixing the waste material with the water, and we were subjecting some kind of temperature, let's say 180 degrees C to 350 degrees centigrade, depending upon the selected waste material. And we were providing some initial temperature of 20 to 40 bars, and we were obtaining aliphatic or aromatic hydrocarbons. But when we tried this technique for a complex waste, for example wind turbine blades and for PV panels, this technique, hydrothermal treatment, was not suitable or was not working for this kind of waste. So we decided to introduce a third character in the story. So now in oxidative liquefaction, we have water, waste material, and also the oxidants. and we are using the almost less temperatures or almost equivalent temperature to the hydrothermal treatment. For example, 150 to 350 degrees centigrade, same initial pressure 20 to 40 bar. But now this time we are expecting to get, instead of aliphatic or aromatic carbons, we are expecting to get some kind of oxygenated chemical compounds, mostly the fatty acids. So selected waste materials, again, end of life wind turbine blades and end of life photovoltaic panels. And how this oxidative liquefaction actually works in a laboratory scale, or in our laboratory, there's some kind of representation from our experimental setup. So here are different 7 steps are mentioned for the process, including sample preparation, like very basic reactor loading, inert gas purging similar to the pyrolysis, temperature and pressure control, oxidative liquefaction, that is the main process, and process monitoring to obtain the real-time data from our reactor or our system, and then product separation at the end. So we are selecting with the waste material that is mixed with the hydrogen peroxide and water, as mentioned here in the equation also. And this sample is going to the PAR reactor, that is high pressure and high temperature reactor, that has almost the capacity of 350 bars of the pressure, and it can also reach almost 400 degrees centigrade. And this reactor is controlled by the power reactor controller, and this control is connected with data acquisition device from National Instruments NI, and then we have a software interface that is actually showing us what is happening inside the reactor, how the temperature is changing or how the pressure is changing. And we connected this data acquisition device NI externally to this reactor, so we can actually monitor, or we can actually store the real data from the reactor, from inside the reactor, to see how the temperature is changing inside the reactor with the time. We were not only focusing on initial or final temperature, but we were actually focusing on point to point temperature for the duration of every 5 seconds. So end of the process, we definitely have 2 kind of products. One, oxygenated chemical compounds that were actually some kind of liquid that was subjected to the GCFID, gas chromatography with flame ionization detection, to see what exactly we have in this liquid section. And there was we have the solid residual fraction. So this solid residual fraction in the case of wind turbine blades, as I said, could be the glass fibers. And so I talked about oxidative liquefaction and experimentation. So before performing the experimentation, we decided to plan a detailed experimental matrix. So we should have a proper scheme that how we're going to perform this experiment. So for this purpose, we uses 2 kind of design approaches: central composite phase center plan, and we also use central composite design plus fractional factorial design. So in the case of wind turbine blades, so during the process, we tested 5 different parameters that are mentioned in the table, starting from temperature, pressure, waste to liquid ratio, residence time, and oxidant concentrations. These -1, 0, and 1 are actually the coded values against the levels of these tested parameters. And for wind turbine blade, you can see we started from 250 degrees centigrade of temperature, then 300 degrees C, 350 degrees C. So for the pressure was 20, 30, 40. Waste to liquid ratio was 5, 15, 25 percent. Residence time 30, 60, and 90 minutes. And oxidant concentration was 15, 30, and 45. So first we performed the experiments with the wind turbine blades, following the whole central composite phase center plan, and we performed almost 29 experiments, including some repeated runs to calculate the error and the standard deviations. But we noticed during our experimentation for the wind turbine blades, this pressure and the residence time has the minimum effect on the process output. So we decided to choose now the less factors and follow the fractional factorial design. And for this purpose, we only this time considered temperature, waste to liquid ratio, and oxidant concentration, including pressure and the residence time, were kept constant at 30 and 45 minutes for the PV waste. So based on these conditions, we performed the oxidative liquefaction process. So as I said, during the oxidative liquefaction process, we were recording the temperature for every 5 seconds inside the reactor. with the interval of every 5 seconds to see how this reactor is actually changing, because we were expecting this oxidative liquefaction process somehow to exothermal, because we are using hydrogen peroxide, and actually when hydrogen peroxide around you can say 100 degrees or maybe 120, 130, it's decomposing and it's releasing a lot of heat and energy. So we were expecting oxidative liquefaction to be somehow exothermal, and this was proved here when we plot the time on the left side of the graph, when we plot the time on the x-axis and the temperature inside the reactor on the y-axis. And this, there were three kind of runs were performed only when we heated the water, that is called dummy run with the water only, and you are seeing there is no bump, and this is like a smooth curve going from 0 to 200 degrees centigrade. But in the case of PV waste, when and dummy run with the oxidant, you are seeing there is a bump appeared in the with the lines black and with the lines blue. So it seems some additional temperature rise happened. This rise was not existing when we used only heating the water in the reactor. So it seems around 30 to 50 minutes of the time of the reaction, we have some additional heat appeared, that is maybe due to some kind of chemical reaction. So for this, to make it more clear, we just plotted temperature inside the reactor against the change in the temperature per minute, so means heating rates. So in the case of water, that is on the right side of the graph, you are seeing these blue lines. These are small, you can see peaks, but these are not like these small fluctuations, but there is no big peak, or there's a no very differentiable or very big peaks happened when we were heating the water. But on the other hand, you are seeing there are big peaks in the case of red lines and the black lines for the dummy run with the oxidant and dummy run with the PV waste appeared. So it means this already increased heating rates in the case of dummy runs with the oxidant and PV waste means that additional heat is actually supplied during the process, that was from the decomposition of the hydrogen peroxide in combination with the PV waste. So we can say during the oxidative liquefaction, some additional heat is supplied by the reactants itself, but this heat is not sufficient enough to carry out the reaction by itself. So we have to use some energy as a source or input. So after seeing some process or seeing some internal details from our reactor, we decided to check our process parameters to see how good is our process. So for this purpose, we used to calculate total polymer degradation. So it's important to note that we are not talking about total solid degradation. We are only talking about total polymer degradation, because we are not capable of degrading the glass fibers, and we don't want to degrade them because we want to obtain them. So we will trying to degrade the polymer matrix that is mostly existing in wind turbine blades and in PV panels. So you on the left side, you are seeing we performed almost 19 experiments, and for wind turbine blade we mostly performed 29, but for here, for the comparison, I'm showing the 19 experiments. And on the y-axis we have total polymer degradation that is compared here, both for the wind turbine blade and PV waste. And you are seeing for the in the black lines for the wind turbine blades, we have higher concentration of or higher yields of total polymer degradation than PV waste. In some of the experiments, like during the experiment number 5, we have some comparable and high polymer degradations, mostly reaching the 100% and leaving only the intact glass fibers and the recoverable materials on the back. But mostly the polymer degradation for PV panels was less as compared to for the wind turbine blades. And on the right side, we decided to check the acetic acid yield in gram per kg of waste. So you are seeing for the wind turbine blades, against the number of experiments we performed, we got very high concentration of almost of acetic acid, and it was reaching to 25 grams per kg of the waste in some of experiments. So these yields again for the acetic acid were comparatively higher for the wind turbine blade waste as compared to a PV waste. The main reason I will talk here is because in the case of wind turbine blades, we have more polymer existing, for example, polymer concentration, for example, 70%, as I showed during the ultimate and approximate analysis, and the less concentration of the ash. But on the other hand, we have in the PV waste, we have very high concentration of ash, means inorganic materials that are not subjected to the degradation. So we have less results or less values for the polymer degradation and also the less value for the acetic acid yield. So here on the screen, you can see, as I talked, from the wind turbine blades, we have this possibility to recover the glass fibers. So you can see on the screen the same images of the recovered glass fibers and also some normal images for the glass fibers that we obtained in the lab. So you can see on the left side in the same images that we have only just like one layer of the material in which there is everything, this polymer matrix, there is also the glass fibers, and they are in the form of one sandwich, or they are in the form of the one layer. But on the right side in the same image, you are seeing that we have very clear and very continuous and intact glass fibers that were obtained during the oxidative liquefaction of wind turbine blades. So that is actually supporting the concept of recovery of useful materials for secondary applications. Till now, we just talked about very simple things and about calculating polymer degradation, calculating yields from liquid products. But now we will just shortly talk about statistical analysis of the results, because as I said, we were using the reactor and this reactor was consuming the energy also. So we need to identify the values of these parameters that are optimum for performing this oxidative liquefaction process. And this was done by performing the analysis of variance. And if you will see here on the graph, I am mentioning the same parameter: temperature, pressure, oxygen, and residence time, and waste to liquid ratio. And you are on the top, you're seeing yield of oxygenated chemical compounds and its behavior against the increasing temperature, increasing pressure, oxygen residence time, and the waste to liquid ratio. The second graph is showing the yield of total polymer degradation obtained in percentage, and you're also seeing its behavior against the increasing values of tested parameters. And then we are seeing the energy consumption on the third line, and we are seeing how this effect is changing when the parameters are changing during the process. And later on the fourth row, we are seeing the desirability of these parameters, desirability of increment in these parameters. So here, very shortly, these red lines are actually showing the optimal values of each parameters that should be used to obtain the best results. For example, I will just talk about shortly about the temperature. So if you are seeing, when we are increasing the temperature, the oxygenated chemical compound yield actually decreases. And on the other hand, the yield of total polymer degradation is increasing. But with the increase of temperature, you're seeing that we have very high rise of the energy consumption. So as compared to this rise in energy consumption, over total polymer degradation is not increasing as it should. So we decided on like for the optimum condition for this temperature could be the minimum values of temperature, because of the increase of temperature, first over energy consumption is increasing, and second over oxygenated chemical compound yield is decreasing. So the least values of temperature are sufficient for obtaining the best results from the oxidative liquefaction of wind turbines blade. Similarly, you are seeing for the pressure that this pressure with the increase of pressure, this oxygenated chemical compound yield is increasing somehow, and then later but on the other hand, this total polymer degradation has no effect with the increase of pressure. So that's why in the next for the PV waste we didn't consider this increasing pressure. So these red lines are again showing the desirable values of these parameters. And then we have same for the oxygen. You can see that how if we are changing the oxygen concentration in the reactants, how the products how our process outputs gonna react. So in the similar way, we just tested for a whole of these process parameters and we checked their response against the changing process variables or reaction variables. So on the right side, if you will see this colorful graph, it's actually showing the combined desirability of two parameters during the process. Let's suppose if we want to check the response surface against increasing temperature and increasing pressure, and we want to see the desirability of these two parameters together during the process. So we can see the increasing temperature. For increasing temperature, this this surface has a curvature and it's going down to the lower value. So you can see the desirability of increasing temperature is less, while almost the desirability of pressure is somehow higher in the center, but on the corners it's just like a curve. So the desirability of the high or the low pressure is low, but in the center the desirability, like the central values of the pressure, are more desirable during the process in the bigger terms or on the bigger scale. So very similar way in the lower graph, you are seeing the desirability comparison, you're seeing the comparativity of desirability for the residence time and hydrogen concentrations. So you are seeing the least values of both residence time and least values of hydrogen peroxide concentrations are less desirable, just like an umbrella that is higher in the center but lower in the corner values. So means we have, in like broader scale, we have to use somehow intermediate residence time and intermediate values of hydrogen peroxide if we want to get the best results. So we talked about.
Sorry to interrupt you, Hamza. The time. Please wind up
Okay. Yes,
within 5
okay.
minutes.
Yes, I got it. So we are just finishing because we have only 1 or 2 slides remaining. So in the similar way, we have performed analysis of variance for identifying the optimal reaction conditions for the PV panels, and same approach was used as in the previous slide. So analysis variance were performed to see the effects of different parameters on the process outputs. So in the conclusions, if I will conclude shortly, we have sufficient results to say that oxidative liquefaction is a technique that has a potential to recycle these wind turbine blades and recycle these complex PV waste materials. So intermediate, I will say again, these intermediate values of pressure and the residence time were desirable, but the minimum values of temperature include from 200 to 50 degrees C are the best values to obtain the maximum process outputs. So the process efficiency is influenced by the composition of the waste, is highly dependent upon the composition of the selected waste. So, and it also depend upon the homogeneity or inhomogeneity of the mixture. So it's very important to focus on the concentration of the sample that we are preparing. So higher oxygen concentration somehow enhance the polymer degradation, but they adversely affect the synthesis of oxygenated chemical compounds due to the over-oxidation, and lower waste to liquid ratios are always preferable in waste to liquid in oxidative liquefaction process. And these are actually this work is actually till now is on the laboratory scale, but we are performing some more processes, for example, LCA and other estimations to just support its application on the industrial scale. So during the first slide, I showed some graphs. So these were the references from which I took the information for this graph. So at the end, thank you for your kind attention and the valuable time. And I am stop sharing my screen, and thank you.
Thank you, Dr. Hamza, for such an interactive presentation and insightful talk. Thank you very much.
My player. So any questions?
Any questions from the house? Thank you, Dr. Hamza.
So thank you, and thank you again to everyone, and bye bye. I wish you the good time at the UIT Lahore.
Jazakallah. Our next speaker is Dr. Imran Zahid. Dr. Imran Zahid joined GCUF as an assistant professor in the Department of Mechanical Engineering, where he has served as postgraduate coordinator, academic coordinator, and industrial liaison officer, promoting academia, industry collaboration, and student internships. He did his PhD in mechanical engineering from UIT Lahore, focusing on nano enhanced phase change materials for cooling electronic components. Dr. Zahid's research covers heat sinks with nano enhanced phase change materials and hybrid glass carbon Kevlar fiber composites for lightweight automotive applications. He has published multiple indexed papers, contributing book chapters, and served as a reviewer for several elsewhere journals. His experience include XRD, TGA, BIRD, and SEM EDX techniques. Let's welcome Dr. Zahid for the talk titled Thermal Analysis of Mini Heat Sinks Using Nano Enhanced Phase Change Materials. Dr. Zahid, welcome. Dr. Zahid, we didn't hear you. Dr. Zahid, I again ask, we didn't hear you. Please open up your mic, Mrs. Zahid. ये म्यूट तो नहीं है? It's like we didn't hear you. नेक्स्ट कैंडिडेट को करके हैं। हाँ, नेक्स्ट कैंडिडेट को ही जगह देके ना। बस ठीक है, उनको दे देते हैं। इसे अभी आप लौटा कैसे दोबारा ज्वाइन करें। Assalamu alaikum, Dr. Zahid. Please talk. Please, still, there is a problem in the mic. कॉल पे ही अब अपना स्पीकर Thank you. But I'm not sure. I would also like to get some thoughts from